today is to talk about going from a generator potential to an action potential. We'd started a little bit of this last time, but what I want to do is lay out an imaginary primary sensory afferent. This particular primary sensory afferent will be activated by a change in the shape of the input region of the neuron. And so what we're going to do is change the shape of the input region of the neuron, and in so doing, we're going to generate a new kind of potential called a graded potential. That graded potential is going to result from the mechanical opening of the so-called stretch-activated channels. So the stretch-activated channels are these special kind of transmembrane proteins across the membrane of the input region of the sensory neurons. When we deform the membrane just a little bit, we'll tug open these channels. When the channel opens, sodium comes in. Now this sounds pretty familiar because we've talked about opening sodium channels and allowing sodium to come in, but those channels were gated by charge. They were gated by the depolarization. These are going to be a new kind of channel that are now gated by changing the shape of the membrane. We change the shape of the membrane, we open these channels, and sodium comes in. Now, this is an important idea, what I'm going to say right now. The voltage-gated channels that we have talked about up to now have a threshold. Once we get enough positive charge in around the cytoplasmic sides of those channels and they open, they communicate to the neighboring channels. Everybody opens almost at the same time. They are all or none. They're open explosively. These electrical signals generated by the stretch-activated channels, those signals are proportional. The amplitude of those signals is proportional to the number of the stretch-activated channels that open. Now, that's a long-winded way of saying we have two kinds of signals here. The action potential signals, all or none. If you reach threshold, you're going to have it. It's always going to be the same. But the graded potential is different. The graded potential, the amplitude of the graded potential depends on the number of these stretch-activated channels that open. The more we open, the bigger the depolarization. From that, we can say that the signal is proportional to the strength of the stimulus. The more stimulus, the greater the depolarization. But one of the ideas here I want to drive home when we draw this neuron and put it at the tip of your finger is that there's a long, long distance between the tip of your finger and the central nervous system where the other neurons that this sensory neuron will communicate happen to live. And that this graded potential, as we saw at the beginning of yesterday's lecture, this graded potential can't propagate this great long distance because it isn't activating voltage-gated channels. In other words, the stretch-activated channels themselves can't signal over long distances. That signal generated by this opening of the stretch-activated channels has to now open voltage-gated channels that produce the all or none action potential. So it's a sequential event. Graded potential provides adequate positive charge to open voltage-gated channels that now initiate an action potential that propagates along the conductal region into the central nervous system. And this is typical. Over and over again, we'll see a graded potential to an action potential. And we'll talk about this first in terms of these generator potentials in sensory neurons in the periphery, and then we'll bring that idea into synaptic potentials. So remember that when we talked about the neuron doctrine, we said the nervous system is formed from individual structural and functional units called neurons. And that for these neurons to communicate one with another, there needed to be some kind of site of communication. That gave rise in the early part of the 20th century to this enormous argument whether neurons communicated one to another by chemicals. This school of thought was called SOUPs. And another group that said there's actually an electrical connection between individual neurons. Those guys are called sparks. So the SOUPs and sparks had these arguments that went on for years. SOUPs won. And I'll give you a little bit of a history of how that came about. So initially, there was the concept that there needed to be a site where one neuron would communicate to another, and that initiated a term that is called the synapse. The synapse is simply Greek for to clasp or to hold. So initially they said there must be places where these two cells are holding on to one another. And that was the genesis of the term synapse. But then the question is, are there direct electrical connections here, or is it a chemical released from one cell talking to another? The first indication that it was chemical is the description of a so-called receptor substance. There was another scientist almost at the same time who was a pharmacologist, and he established that, particularly on muscle, there was a receptor substance. But we'll see that the receptor substance was for nicotine, and of course, animals don't have nicotine. It took another round of experiments, some 15 years later, which showed that it was chemicals. It was a neurotransmitter being released from one cell to activate the next cell. And we'll walk through that history. Then, if there's time, we'll talk about the structure of the synapse. The synapse is composed of an output region of one neuron, we'll call that a presynaptic element, and the input region of a neighboring cell, neighboring neuron, we'll call that the postsynaptic element. And then there's always a mechanical gap, a separation between the presynaptic cell and the postsynaptic cell called the synaptic cleft. And we'll draw that out. But we're going to spend a fair amount of time on how we manage to regulate the release of neurotransmitter from the output region of one neuron onto the next. And there are a number of characters we'll talk about here. In the presynaptic element, we're going to find that there are synaptic vesicles. These vesicles are filled with 5,000 to 10,000 molecules of neurotransmitter. We'll find that in the plasma membrane of these cells, they'll be clustered at certain sites. They'll be clustered the voltage-gated calcium channels. And along with the voltage-gated calcium channels, we'll find that the vesicles are going to nestle up against the membrane at a site called an active zone. So the sequence of events is the action potential arrives, depolarizes the membrane, opens voltage-gated calcium channels, calcium comes in at the active zone, and triggers the exocytotic event, where there's exocytosis of the synaptic vesicle with the plasma membrane to release the neurotransmitter. In 2012, this sequence of events, the molecular understanding of the sequence of events, was awarded the Nobel Prize for the snare hypothesis, and we'll talk about that. The fate of the neurotransmitter, then. What happens to the neurotransmitter after it's released? Well, one thing it's going to do is it's going to bind to receptors on the postsynaptic cell. And when it binds to the receptors on the postsynaptic cell, we'll see this going to open channels. But in addition to binding to the receptors, that neurotransmitter, after it's bound to the receptors, as we've discussed earlier, can be taken back up into glial cells, sequestered back into glial cells. And the third thing we're going to see, mostly in the peripheral nervous system, as the neurotransmitter can be broken down by enzymes that are designed that are there to break down the neurotransmitter. And then finally, if there's time, we'll talk about the effect on the postsynaptic cell. But I want to begin here with the idea of generator potential to action potential in a stretch sensitive sensory neuron. Before we drill down into that, let me show you quickly here a couple of pictures that really summarize where we were last time. Now, this first one shows more detail than I described. And for those of you who have a physics or engineering background, you'll look at these curves and you'll say immediately, that's an exponential decay. Fair enough. What it's showing is that if we put charge in across the membrane at one point, that this charge now will leak out across the membrane through the leak channels. The decay is going to be a natural log, but don't worry about that. All I want to demonstrate here is that if we produce a depolarization at this site, as we move away from the site of depolarization generated by putting positive charge in the membrane, that amplitude of that potential is going to decay with distance because the current, the charge, will diffuse out of the membrane through the leak channels. So the potential now gets smaller and smaller with distance, and these distances are relatively tiny. Typically, the distance to which this thing is going to decay, particularly here in an unmyelinated axon, is going to be a couple of millimeters. It goes down about 30 millivolts. Now, the only reason I'm showing this is to emphasize in a graphic form that the potential gets smaller with distance because the charge is leaking out of the membrane through the leak channels. That's an important concept to hold on to. So this was effectively the story we told by clustering the voltage-gated channels at one end of the axon and having only leak channels along the remainder of the axon. This is a demonstration of what happens when we now begin to distribute those voltage-gated channels evenly all along the membrane. So this is an example of an unmyelinated axon. And what they're showing here is the charge on the outside of the cell and the charge on the inside of the cell. We established this as the resting membrane potential, saying the inside of the cell is more negative with respect to the outside. And then when the voltage-gated sodium channels opened, then what would happen is there would be a reversal in the potential across the membrane. So where initially it was positive on the outside and negative on the inside, because of the influx of sodium, the polarity changes. It's now negative on the outside and positive on the inside. So what we're looking at here in this region depicted in red is the depolarization of the membrane by the opening of the voltage-gated sodium channels. But then remember that we open those voltage-gated sodium channels only briefly. Then the ball and chain moves into place, the channel becomes inactivated, effectively closed, and then the voltage-gated potassium channels open. So then when the voltage-gated potassium channels open and remove the positive charge, then we go back to the old situation of positive on the outside and negative on the inside. And by doing this sequentially, we can roll down that membrane, roll along the membrane, sequentially opening voltage-gated sodium channels and potassium channels and propagating the action potential along the membrane. What this figure shows that I didn't describe, and what it shows in yellow, is a region that is said to be refractory. In the refractory region, it's more difficult for a time to initiate a new action potential. But you know, if you look at this for a little bit, if you can apply what you've already learned, you can begin to recognize where that refractory period comes from. The refractory period results from the fact that during this short interval here, behind the propagating action potential, there'll be two cases that are important. First, you'll notice that those voltage-gated sodium channels will be in the inactivated state. So if you put your phone away, I'd appreciate it. 1, 2, 3. Thank you. And so that now, just behind the propagating action potentials, those sodium channels are now going into an inactivated state. But at the same time as those channels are closing or inactivating, the voltage-gated potassium channels are opening, and so now you have a region of high potassium permeability. Because of the high potassium permeability driving the membrane potential just about to the equilibrium potential for potassium, you have the two effects. One is the increased potassium permeability and the lowered sodium permeability that are in this yellow region, reducing the chances of your ability to generate a new action potential. That's the refractory period. And this is a summary slide of where we left off. This is a summary slide of propagation of action potentials in a myelinated axon. So remember that all of the sodium channels are clustered at these naked membrane regions called the nodes of Ranvier. When we open these voltage-gated sodium channels, sodium comes in. What I don't like about this figure is it implies that these little dots, these purple ping pong balls, are taking a walk down to the next node, and they don't do that. The sodium ions, as they come through the voltage-gated sodium channels and arrive in the inside of the cell, carry with them an electromagnetic field. That electromagnetic field is then almost instantaneously propagated through the axoplasm, through the conductal region of the salt solution to the next node. And it's that electromagnetic field now which is telling the next set of voltage-gated sodium channels to open. So you don't need to have the actual sodium channel nestling right up against the cytoplasmic side of that channel. You can use the electromagnetic field of these ions to open the next set of channels. The other point that this doesn't show very well, but we emphasized last time, is that by making these concentric rings of myelin, by wrapping the membrane with myelin wrap after myelin wrap after myelin wrap, we now separated mechanically the inside membrane of the axoplasm with the outside world. And what that did, that separation, that distance of separation, then made it difficult for the ions way out here to interact with their electromagnetic field with the ions on the inside of the plasma membrane. And we called that capacitance. We said when we had only that very narrow 6 to 7 nanometer width of a membrane, that was a tremendous capacitor. That the hydrophobic tails of those phospholipid bilayers were practically impervious to the movement of ions, but the electromagnetic fields could reach across that hydrophobic region and interact with ions of the opposite charge on the other side of the membrane. That's capacitance. The capacitance is pretty high right here in the nodes because we only have that exquisitely thin layer of plasma membrane. But because we have all the insulating wraps in the internodal region, the capacitance in here is terrible. We say it's terrible, but in fact, that's really good news for the action potential propagation because it means that the ions coming in at this site don't have to expend very much energy to offset or take up the charge to deactivate the charge along this region of the membrane. So the ions come in and the sodium comes in and they only have a relatively few number of negative charges to offset. So most of the electromagnetic field coming in at this site can be brought to bear on the cytoplasmic side of the voltage-gated channels at the next node. And that was the crux of how we increased the rate of propagation. That we didn't have to spend all that energy sequentially sopping up the negative charge on the inside of the membrane. We could now, because of the lack of charge here, move the potential rapidly from this node to the next. Yes?
So there's something, I might butcher this, there's something in the ether in my brain that I'm going to try to reach in and grab, and it may come out right.
I'll see if I can help pull it out.
So the location of potassium channels. A bunch of us had this discussion, there's a good handful to have this discussion. Location of the potassium channels under the internodal region.
That's truth, and I told it to you because it is truth. But for our purposes here, it doesn't much matter. All right, so you do need to have potassium channels, all right? So the potassium channels are absolutely essential for repolarizing the membrane. And for a long, long time, we thought we'd put the voltage-gated sodium channels, the voltage-gated potassium channels out here intermixed. We thought we'd just put them out there because they would always be one with another. And then people began labeling those channels with fluorescent dyes. And they found, sure enough, that if they had green sodium channels, they were out here. But if they had red potassium channels, they were always tucked up underneath they were always tucked up at the edges of the nodes of Ranvier underneath the myelin.
What is the purpose in that?
What's the purpose for that? Fair enough. So what we think the purpose is that when the potassium channels open right at these edges, right under these, what they call these terminal loops of the myelin, that now that potassium goes out of the axon. But rather than going directly into the extracellular space, it goes into the oligodendrocyte. And then all of these terminal loops in here, all of these are connected one with another by gap junctions. So now this gives a pathway where the potassium never gets to the outside until it passes through all those loops and gets to the top. The functional reason for that isn't quite clear, but I'm pretty sure the functional reason is that if you mixed in here the potassium channels and allowed the potassium to flow out into the node, this is a confined region. It's not very clear from here, but if you would shrink yourself down to these dimensions and you would come to the node, you would look down into a great valley. And so this would be a great valley down below you. And at the bottom of that valley would be this membrane. So now this becomes a confined volume. So that if the potassium channels were here in the nodes and they open, they would now deposit potassium in that confined volume. You then begin to build up the potassium concentration on the outside of the membrane. Now we're back to the Nernst potential. It's the log of the potassium concentration on the outside of the concentration inside. So now you begin changing the concentrations out here very much and you polarize the membrane. If you polarize the membrane, excuse me, If you depolarize the membrane, you'll kick those sodium channels into the inactivated state, and you can't conduct an action potential. So the story is much simpler if we simply cluster the voltage-gated sodium channels and the voltage-gated potassium channels at the same spot. But reality says that for this thing to function properly, we have to provide a site where we can remove the potassium, not just into the extracellular space, but at some point far away from the node. And we do that by passing it through these terminal loops of myelin in the oligodendrocyte. That's how we think it works. Yes?
So I'm going to butcher the word, oligodendrocyte,
right?
Is a phospholipid bilayer.
Well, the oligodendrocyte's a proper cell, remember?
Well, but the wraps, myelin wraps.
Right. Fair enough, yes.
So how does potassium pass through that?
So that's a great question. We're getting behind. But no, I'll tell you the story. And it's a little unclear. There's someone in the department who's still working on this. But it looks like there are specialized junctions. There are specialized junctions directly between a potassium channel and a gap junction. And they're really weird, unusual, and maybe just hypothetical junctions. So that when the potassium leaves out through the potassium channel, it's mechanically linked to a gap junction channel, a half a gap junction channel. It's not a proper gap junction, because remember, you need two connexons. So it's one connexon connected to a potassium channel. And the thought is then the potassium goes out through that potassium channel, through the connexon, and into the cytoplasm of the oligodendrocyte. But you're absolutely right. You need to have another route for that potassium to go down its concentration gradient. And the only way you can do that, it appears, is to have this mechanical linkage. But that's hypothetical at this point. We don't know for sure. Right? Anything else? Yes?
So at the nodes of Ranvier, there's only sodium channels?
So at the nodes of Ranvier themselves, at the naked region of the membrane, there are only sodium channels. But right at the boundaries, tucked up beneath the oligodendrocytes, there you find the potassium channels.
And the sodium that comes in doesn't actually move?
The sodium itself does not have to take a walk.
So it just sits there and shoots its positive charges out?
It has electromagnetic field, right?
Like, how does it move that across though? Those only interact in a small area.
Well, it's depending on how conductive the medium is, it will more effectively go down to the next node. And again, it's hard to get your head around this, but try playing with a magnet. So take two magnets, positive, take the two south poles. You bring them together, and then suddenly you reach a point where you can't get them any closer together. That's the electromagnetic field. So as you have an electromagnetic field in a magnet, each of those ions carries with it an electromagnetic field. So they can give an action across a distance through a conductive medium. The conductive medium being the salt solution of the axoplasm. Right? What else? Okay. On to generated potentials. So let's start out, and I'll draw a hand here, and truth of the matter is, it's even worse. The truth of the matter is there are better looking hands on the caves drawn by Neanderthals than I'm going to draw here. That's a hand. Out here is going to be the input region. This is an input region of a stretch sensitive. Neuron. Well, let's exaggerate that a bit and take this as the nerve ending. This is the input region of the sensory neuron. So out here in the input region of the sensory neuron, we're now going to find a new set of channels. I'll put these guys in purple. These are stretch activated channels. These stretch activated channels have gates on them. So you can imagine a gate down here. But the gates, I'll put it in black. The gates are opened by mechanical stretch. So you can imagine reaching out and touching something. You can imagine changing the shape of the end of your finger. When you change the shape of the end of the finger, you actually change the shape of this plasma membrane. When you change the shape of the plasma membrane, you tug on the membrane, and when you do that, it opens a pathway for sodium to come in. So, as we've graphed before, if we graph time and voltage, we set a resting membrane potential of minus 70 millivolts. It's stable. Now at this point, we begin to pull on the membrane. So we pull on the membrane, and by pulling on the membrane, we open some of those stretch-activated channels, and we get a little bit of depolarization. We tug on a little more, a few more of those channels open, and get a little bit of depolarization. We tug on a little more, we get a little bit more depolarization. Now, one of the ideas I want to point out here is that the amplitude of the depolarization, produced by stretch-activated channels is proportional to the number of channels that open. What's more is that the stronger the stimulus, the stronger the stretch, the more channels open. So what we're saying here is that the stronger the pull on the membrane, the more of these channels we open. The more of the channels we open, the greater the depolarization. We can say that the response, the depolarization, we should even say the amplitude of the repolarization, is proportional to the strength of the stimulus. Now, some of you have taken some other courses will recognize it is not direct, it's a logarithmic arrangement, but regardless, the more we pull on the membrane, the more ions come in, the greater the depolarization. But if all we had between here and the central nervous system, let's see if I can draw this in. So we would follow this conductile region of this primary sensory afferent across your wrist, up your arm, and then here, it's going to enter the central nervous system. This is meant to be the spinal cord. And in the spinal cord, we'll find that this sensory afferent will have a cell body out here, in a site called the dorsal root ganglion. And then a process is going to extend into the central nervous system. And in the central nervous system, there'll be an output region. With that in mind, let's take a moment and look at this next figure. This is a drawing of some generic kinds of neurons. And we've talked about this, so let's just review this. The one on the left is going to be the sort of typical neuron. It's the model neuron. It shows an input region, a conductal region, and an output region. So here's the model neuron of input, conductal, and output. That's pretty much the same as this motor neuron over here, where the neuronal cell body will be in the central nervous system, the process goes into the periphery, and then there's synapses out here in muscle. So again, we have input, conductal, and output. But this is the model of the neuron I just drew. This is a primary sensory afferent. So its input region is out here in the periphery. This was representing its input, its endings out here in the skin, probably at the interface between the keratinocytes and the dermis. Now, what we just drew is shown here with that input region at the tip of your finger. And when we pull on this membrane, sodium comes in. But now could be as much as a meter away. This site can be as much as a meter away from the synaptic sites, the output region in the central nervous system. So this is an input region, this is a conductal region, this is an output region. So this is one of the examples where the archetypic neuron doesn't work very well. The anatomic description of dendrite cell body axon doesn't work very well. Here we have this input region out in the periphery, the cell body's way up by this central nervous system, and then we have another process that goes into the central nervous system. But functionally, we can describe this as input, conductal, and output. And remember, the hallmark of the conductal region is voltage-gated channels. That's what I want to talk about now, because if all we had out here at the ending were these stretch-activated channels, and we put a depolarization in here, if these were the only channels we have, you know from what our initial discussion was last time, is this potential would barely get beyond your first knuckle. Because you need a way of amplifying that signal and carrying that signal over long distances. And of course, the amplification mechanism here is going to be the generation of action potentials. So we can imagine here, right nearby this input region where we have the stretch-activated channels, will be clustered. The voltage-gated sodium channels, along with their counterparts, the voltage-gated potassium channels. But remember what triggers the opening of the voltage-gated sodium channels. It's charge. So now we can answer the question that keeps coming up every time we introduce these voltage-gated sodium channels: where does this positive charge come from? In this particular instance, in this case, the positive charge is coming from the sodium coming across the membrane through the stretch-activated channels. The sodium is positively charged, so it generates depolarization. If we have enough of these sodium ions coming in across the membrane to bring the membrane at this site where we have clustered the voltage-gated channels called the trigger zone. If we get sufficient positive charge coming through the stretch-activated channels to bring the membrane potential to that magical point here called threshold, then we've applied sufficient positive charge in the neighborhood of these voltage-gated sodium channels. They begin to swing open. They then carry more sodium in. They carry more positive charge in, and that then opens the neighboring voltage-gated sodium channels. And now everything, this is going to get messy, goes up to plus 40 millivolts. We fired an action potential. And then again, from what we saw on that first slide today, because these, if this were an unmyelinated axon, which it probably wouldn't be, but because if it were an unmyelinated axon, then all along the length of this axon will be the so-called voltage-gated sodium channels. So now when we open these, we initiate the action potential, and at each point along this membrane, we can watch the propagation of that all or nothing signal. It goes up to plus 40 and comes back again. This is the action potential. So the action potential is now propagating along the membrane, but recognize there's a really stark difference between these potentials here shown in purple from the stretch-activated channels, which are in fact a generator potential. The generator potential is graded with the strength of the stimulus, but once we reach threshold, we have an all or none invariant signal. And that all or none invariant signal is going to go to plus 40 millivolts. The sodium channels will inactivate, potassium channels will open and bring the membrane potential back down again. Yes?
What happens in the trigger zone?
So what happens in the trigger zone? What happens in the trigger zone results from the characteristics of the voltage-gated sodium channels and the fact that they're mechanically clustered at this point. Remember the S4 region on the voltage-gated sodium channels. So what happens is the positive charge brought in across the membrane through the stretch-activated channels will move those S4 regions. And we move 3 of the 4 S4 regions on the voltage-gated sodium channel, it opens. The gate opens, sodium comes in. So now we're beginning to amplify the effects of the sodium coming in through the stretch-activated channels, and that amplification is to open the voltage-gated sodium channel and start the propagation of the action potential. But it's that positive charge initially delivered by the graded potential produced by the stretch-activated channels which opens the voltage-gated sodium channel. Okay? And you had a question earlier. Never mind that. All right. So the input region, this is actually, in many cases, this will be surrounded by another cell that amplifies the effect, but let's not get into that. Anything else? Yes?
So you said that the stretch-sensitive neuron is most likely unmyelinated?
No, in fact, the stretch-sensitive neuron is almost certainly going to be myelinated. Among these stretch-activated channels, we have the greatest myelination of anywhere in the body. But I wanted to simplify it, simply to emphasize that we could now have voltage-gated sodium channels all on the length to generate the action potential. But you're right. In reality, these voltage-gated sodium channels will almost certainly be clustered at intervals called the nodes of Ranvier, and the action potential would hop from node to node because of that. Anything else? Yes?
Your graph is reflective of myelinated, not unmyelinated, then, right? The little AT graph you do, the action potential graph.
Here?
No, on the far right.
It wouldn't matter for the generation of the action potential. The action potential will be generated whether it's in the same fashion. It's only the propagation of the action potential will be different. But there's an important point you bring up here in that these action potentials are always the same. It doesn't matter if it's in a myelinated axon or an unmyelinated axon or wherever you find them. An action potential always goes from minus 70 to plus 40 and back again. So it opens the question, if these are on or off, digital kinds of signals, how do we use them to signal in the nervous system? And that brings us to this concept, which I'll put in the next panel. And this is the concept of frequency coding. And the summary of this is that action potentials are invariant signals that transmit information from, or through is probably better, through the frequency, let's do it this way, action potential, frequency. Another way of saying this would be action potentials per second. 1 per second, up to as many as 100 per second. And the duration of the bout of action potentials. This always raises the question of what do we mean by a bout. What I mean by a bout is that if we plot this again as time and voltage, if the membrane potential reaches threshold and we fire an action potential, the frequency is how often in this period we fire an action potential. So frequency is how often. It's frequency. But in some cases, this bout will go on for, say, 1 second. Or maybe the bout goes on for 1 minute. So these all or nothing signals, these brief all or nothing signals, which only last about a millisecond or two, the way they transfer information in the nervous system is not by the individual signal so much as by how often they happen and for how long their recurrence happens. So it's the frequency within the bout and the duration of the bout that's carrying the information. Because we have to have some means of signaling over long distances. We go back up here. If we're going to fire action potentials, every action potential looks like every other action potential. But yet what we're trying to do is take that signal and convey that information to the next cell. So what we want to do is convey the information to the next cell at a site called the chemical synapse. We've referred to the chemical synapse earlier, where we describe the output region of this sensory neuron, so this is the output region, at a site where it's going to impinge upon the input region of the neighboring cell. That's the synapse. Now what I want to do, and we're running a little late here, what I want to do now is begin talking about what we mean by a chemical synapse. And I'll start this actually with a little bit of history and describe this as the chemical synapse as the site of interneuronal, meaning between, communication. Shortly after Cajal had convinced most of the scientific community that the nervous system was made up of individual units called neurons, and after he had recognized that the information flow was unidirectional, the law of dynamic polarization. Once that was established, it became pretty clear that there had to be some mechanism whereby one neuron would communicate to another. And one of the early hypotheses was the idea of the chemical synapse. Now, initially, they didn't know there were going to be chemicals. They didn't know whether there was going to be electrical continuity between the cells or whether it was going to be a chemical kind of arrangement. But early on, there was, and don't remember these names, but I need nouns, there was a guy named Sherrington. And Sherrington was working at Cambridge in England. And Sherrington looked at these structures that Cajal had drawn and talked to Cajal, and he came up with the idea that there must be sites where these two cells got really, really close to the other. And he said there's a site where neurons clasp or hold one another. He then went to his classic Greek and he said, to clasp or hold means synapse. So he called these sites where the cells got really close to one another mechanically, he called them synapses. That's where the term comes from. He didn't know what was going on at that synapse, but one of his colleagues, a guy named Langley. Now, what Langley did is Langley was a pharmacologist. So the physiologist Sherrington is generating a hypothesis that there's communication between these cells, but he doesn't know how. Langley comes along and he says, well, I know that nicotine affects tissues. He was interested in the autonomic nervous system, but he was also interested in skeletal muscle. So what he did is he killed a mouse, and he took a muscle and he dissected out a single muscle fiber. So he teased apart a muscle so that it was down to a single muscle fiber. He then came along with a pipette, and the pipette was full of nicotine. And he could now squirt nicotine out onto the surface of the muscle fiber. And what he found when he did this is that it was only in the middle third of the muscle cell, in the region where the motor neuron commonly came down close to the muscle fiber. So when he was spritzing the nicotine onto the ends of the muscle, nothing happened. But when he came close to the site where the motor neuron was innervating the muscle fiber, when he spritzed on nicotine, he got a muscle contraction. Well, what Langley said then is that there is a receptive substance in muscle that responds to nicotine. Well, that's well and good. We know that we have something responding to nicotine, but nicotine doesn't give us all that much insight because we know full well nicotine is a plant alkaloid. It comes from the tobacco plant. It's not part of our own neurons. So it can't be the chemical that's the key to the signaling from the motor neuron to the muscle. So the third character in this play is a guy named Otto Loewi. And Otto Loewi was working in, I have to erase this. So Otto Loewi was working in Austria. He was working at the University of Gans. And Otto Loewi had been interested in the autonomic nervous system, and he had been interested in the effects of the autonomic nervous system on the heart. And so he knew that he could take a frog heart. He could take a frog heart, kill the frog, dissect out the frog heart, put it in a dish, and leave attached to the frog heart the vagus nerve. And he knew that if he picked up the vagus nerve on a set of electrodes, that he could stimulate the vagus nerve to slow the heart. And he reasoned then that if it were a chemical, if it were some kind of chemical coming out of the neuron that would affect the muscle, that maybe what he could do is he could take a little bit of this fluid from this bath and put it into another bath that contained a heart but didn't have the length of the vagus nerve. And sure enough, by moving the fluid from one bath to the next, he slowed the heart. And he named the molecule that did this, in a typical German fashion, V-A-G-U-S-S-T-U-F-F, Wegestoff. Wegestoff turns out to be acetylcholine, and I'll tell you how that got figured out when we come back on Monday.